recording. Okay, please take it away, Emma.
Thanks, Victor. You can see my screen okay?
Yes.
I'll take that. Excellent. Okay. First off, I apologize if I stop and start a little bit because I have a cold. And if you don't know me, which probably most of you don't because this is my first large BCool meeting, my name's Emma Brown. I'm a PhD candidate at the University of Southern Queensland. And yeah, the talk I'm presenting today is called A Rapid Solar-like Magnetic Cycle in the Late F-star HD 75332. And if you're interested, you can read more about this later. Our paper was published in January this year. So first of all, I'll start with the motivation for this study and the study of magnetic behavior of solar type stars. And that's that although the sun's magnetic cycle has been really well observed, it's still not clear to us if cycles like the sun's are typical or not. So we hope that by studying the magnetic behavior of other late type stars, then we can place the sun's magnetism in a stellar context. So some of the key features of the solar cycle are shown mostly in this image from Hathaway. We've first of all got quite regular reversals of the sun's large scale magnetic dipole, which are occurring every 11 years or so. By the time the large scale dipole has reversed once and then it's reversed back again to its original configuration, we call that one magnetic cycle. So that's around 22 years long. And then between consecutive polarity reversals, we have the activity cycle, the 11-year activity cycle. And during an activity cycle, we see active regions moving closer and closer toward the equator. And then another important feature is that chromospheric calcium H and K emissions will vary in phase with the activity cycle. So that makes calcium H and K emissions a great proxy for magnetic flux. So it's based on that calcium H and K variations that we know that many stars out there exhibit solar-like activity cycles. Comparatively, fewer stars have actually had their magnetic fields mapped in detail using a technique like Ztr Doppler imaging. And then even a smaller sample of those have been mapped over multiple epochs, allowing us to understand how their magnetic fields change over time. So far, or until now, I should say, solar-like magnetic cycles have been observed for only 2 stars, Tau B and 61 Cygni A. And what's interesting about Tau B is that it seems to have this really rapid magnetic cycle of only, it has a period of only 240 days. So that means that reversals of the magnetic field are occurring every 120 days or so. And what else is interesting about this star is it's orbited by a hot Jupiter. So there's a 6 Jupiter mass planet orbiting at around 0.05 AU. And that is more massive than the entire outer convective layers of the star, which is, of course, where we think that the magnetic field is generated. So it's been speculated that possibly the rapid magnetic cycle is related to some kind of star-planet interaction, and the presence of this HJ is speeding up the dynamo and Tau B. And that brings me to our target, which is HD 75332. So this is a star that has very similar physical properties to Tau B. In this table, you can see it is, both of them are slightly more massive and slightly warmer compared to the sun. But importantly, it doesn't have any hot Jupiter. So the key question that is driving our study here is, could HD 75332 have a rapid solar-like magnetic cycle like the one we see for Tau B? So we've assessed 2 things, the long-term chromospheric variability of the star and also its long-term magnetic field variability. And for chromospheric variability, we use the S index, which you're probably familiar with. It's the ratio of the fluxes in the calcium H and K lines to the continuum flux either side of the H and K lines. And we have several decades worth of data to analyze the long-term chromospheric variability of this star. So we've got data coming from Navel. We've measured our S indices from Navel spectra and those span the years 2006 through to 2019. We've also taken some published SMCs published by Marco Matag in 2019, and they were derived from TIGA spectra. And then we also combined that with archival data from the Nat Wilson HK project from the years 1966 all the way through to 2001. And we did a period search using the GLS periodogram by Zekmeister and Kerster, and here you can see some of our results. So on the bottom is the time series data, and I fitted to that a function, but I'll talk about that a little bit more shortly. And the colors of the data in this bottom image just show you the different sources. So the red data is from Nat Wilson project, the orange data is from Narvel, and then the yellow points are the TIGA observations. And then at the top, you can see the power spectrum for the S-index, where we should be seeing any dominant periodicities that are there in the data. So you can see that we've detected multiple possible cycles in the S-index. And I'll start with this long one, the 31.5-year cycle. It's possible that this is a real cycle. And certainly when we look at the Nat Wilson data in red, there does appear to be some kind of long-term periodicity here. But it's also possible that this is linked to the fact that we have 35 years of Nat Wilson data and then a bit of a gap. So further long-term observations would obviously be required to determine if this is real, and then of course figure out the exact length of the cycle. Then we have this 3.9-year activity cycle, and actually when I detrained the data by removing the 31.5-year signal, the 3.9-year signal is even more dominant. And with this one, if we look at the observations, so for example, around 1990, we can see the fitted curve here combines 31.5-year and 3.9-year sinusoids, and you can see that the shorter term variability, the 3.9-year sinusoid, does fit the data quite nicely around 1990 in particular. And then in terms of the really rapid cycles or signals present in the data, there's a 193.5-day signal and then a 398.4-day signal. And here I've just zoomed in on a section of the Nat Wilson data and plotted the 3.9-year and the 193.5-day signals against the data. And you can see that that 193.5-day sinusoid does fit the short-term variability really nicely. Comparatively, the 398.4-day signal doesn't. So what we think has happened is it's given that the frequency interval separating these two signals is about 1 per year, probably the longer signal is an alias of the shorter signal related to the annual seasonal observations. So possibly there's 3 independent activity cycles here for this star, which is interesting. So next, in terms of the magnetic field variability, we assess that using the technique of Zeeman Doppler imaging, which I'm sure many of you are quite familiar with, but I will discuss it in a bit more detail for those that aren't. This is a technique that reconstructs the large-scale magnetic field based off spectropolarimetric observations. So we had 94 circularly polarized Stokes sphere observations taken from Narvel from the years 2007 through to 2019. And we were able to split that up into 12 epochs to create 12 maps of the magnetic field. And in this little video clip, kindly provided by Matthew Mengel, you can see the basics of the Ztr technique. So we have our polarization signal there. It's telling us that the polarization fraction of the light or the strength of the magnetic field. And we can also take from that the radial velocity, which allows us to locate the position of the magnetized region on this rotating star. And because we're observing the star as it's rotating, we're then also able to untangle 3 components of the magnetic field, the radial, azimuthal, and meridional components. And the final thing on this slide to draw your attention to is that the Zeeman signatures, or the polarization signatures, you can see are really small. So in practical terms, to be able to carry out Zoom and Doppler imaging, the first step is to do least squares deconvolution. This is a process where we are assuming that the Zeeman signature is basically the same across all of the spectral lines in the spectrum. So we combine as many lines as we can to come up with an average Zeeman signature with an improved signal-to-noise ratio. And then using the LSD profile, we can then reconstruct the magnetic field. And we've done that using the program Ztr, which is a Python code written by Colin Folsom. And he talks about that in his 2018 paper. And ZDI is an iterative technique, and there's two processes that are occurring consecutively. The first is that we are generating model line profiles to match the observed LSD line profiles, and we use a solar model line profile to do that. And then also we're reconstructing the magnetic field from those model line profiles as we go. And we keep refining the model parameters and the three components of the magnetic field, varying those, so that we can achieve a desired minimum chi-squared fit to the LSD profiles, and also provide the maximum entropy image. And basically that just means the image with the least content or the least features that will still provide these model line profiles. And here you can see some of the results. So what you're looking at is 12 sets of ZDI maps from January, February 2007 in the top left through to January 2019 in the bottom right. And I'm just showing the radial and azimuthal components for today. And the opposite colors obviously representing the opposite polarities of the magnetic field. So out of all this data, the key thing to take away, first of all, is that if we just consider the radial magnetic field, there's been a reversal of the large scale polarity of the magnetic field at some point in between January 2010 and October 2011. And it may be that there has only been this one reversal of the large scale polarity over those entire 12 years of observations. Or what we think is much more likely is that there's actually been multiple polarity reversals in between our observations that we've missed. And we investigate this in a lot of detail in our paper. The second thing to draw attention to is for the azimuthal field. We also see a reversal of the azimuthal field between 2010 and 2011. But we also see these additional changes that are occurring at some point between January and November, December 2017. And then also another change between December 2018 and the start of 2019. So it seems that the azimuthal polarity does not necessarily change at the same time as the radial field polarity. And as I said, we think it's very likely that we've missed multiple polarity reversals for this star. And if we just consider the radial component at this point, although we only observe one polarity reversal, our results actually are consistent with reversals occurring in phase with the 193.5 day activity cycle we detected in the calcium H and K. So here you can see I've got in the top plot the observed radial field polarity shown in red and blue, and then I've plotted the sinusoid that was fitted to the S-index data and assumed that polarity reversals might occur at around activity maximum like they do in the sun, and we can see that the observations match up really nicely with what's expected. And actually, even though the azimuthal field does not necessarily change at the same time as the radial field, the observed polarity of the azimuthal field is also consistent with a really rapid magnetic cycle, a 1.06 year magnetic cycle, which is just 2 times the activity cycle length. So in the bottom plot, you can see we've just plotted the total radial and azimuthal fields over the northern hemisphere of the star. For each of our maps, we've phase folded the data for a 1.06 year magnetic cycle, and we find that azimuthal flux cycles lead radial flux cycles by about 26% of a magnetic cycle. And we see something similar in the sun. there's around a 25% phase shift in the sun between the toroidal and poloidal flux cycles. And also a similar lag has also been observed for tau as well. And then another thing that supports the presence of this really rapid magnetic cycle, rather than a long cycle with only one polarity change in 12 years, is the fact that we've observed really rapid changes in the magnetic field geometry in the space of only months. So here you can see a confusogram. It's showing the field properties that we've derived from Ztr Doppler imaging against S-index cycles. We've plotted a function that combines all three of the S-index cycles we detected. So symbol size here is scaling with magnetic field strength. Color is related to the fraction of magnetic energy stored in the poloidal field. So the more red markers have a stronger poloidal field, whereas toward the yellow and the blue markers, we're seeing a more significant toroidal component. And then the shape relates to the axisymmetry of the poloidal field. So an octagon would be representing a very axisymmetric poloidal component, whereas a really pointy star indicates a non-axisymmetric poloidal field. So one thing we see is that generally the field is relatively simple at activity minima. So for example, around 2010, we're seeing a mostly poloidal and axisymmetric field. And then the other thing that's really important is we've got a couple of pairs of close together observations, just a few, that seem to have occurred within one activity cycle. So for example, in late 2011. And we see that as the S-index increases, the field strength also increases, the toroidal component of the magnetic field increases, and then the axisymmetry of the poloidal component decreases. So all of those things are reminiscent of the solar cycle. And we see similar behavior as well later in 2016. So this seems to be a repeating cycle.
3 minutes.
Thanks. Sandra also showed in her study of tau that there was a similarly strongly toroidal non-axisymmetric field during activity maxima. So our conclusions are that He75332 appears to have a rapid magnetic cycle, and additionally, possibly 2 independent longer period activity cycles. So this tells us that rapid magnetic cycles could be common amongst stars that are similar to HT75332 and tau, and possibly related to their thinner convection zones. And that makes them ideal stars to study solar-like magnetic behavior, because we can study it in a very short time period. And the final thing is that this tells us that tau's rapid cycle is probably not related to interaction with its hot Jupiter. There's one more thing I want to talk about, ongoing work, before I finish. So at the moment, I'm working on a study of chromospheric activity and magnetic field strength, longitudinal field strength, for polar-based stars. So we've been able to measure the S-index, or the R'(HK), and longitudinal field strength for about 600 late-type stars that all have spectra in polar base. And we're doing this study to compare activity with field strength and their variability amplitudes as well, to diagnose dynamo properties. And you can see in our HR diagram, we are including stars from the pre-main sequence to the main sequence, and also more evolved stars as well. And then we also combine our results with published data. So Sudeshna's much larger compilation of activity data from her 2018 paper, and also published ZDI results, so that we can compare activity with stellar properties and large-scale magnetic field geometries. So hopefully you will be able to read that in the coming months. And that's all from me. So thank you for listening, and I welcome any questions.
Thank you, Emma. I'll clap on behalf of everyone else, at least audibly. So yes, as I mentioned at the beginning of the talk, if you have questions, then please either raise your hand or say so in the chat, and I'll call on people to unmute and ask them. I'll just give you a second to do
Maybe
that.
I can ask a question.
Sure.
Yeah, go for it.
Hi, Emma. That was a very nice talk. I was just wondering, did you also look at the dipole strength of the star as well and see how it varied over the whole cycle or the cycles that you see?
We did, I believe. I haven't got a plot or anything to show you, but we looked at dipole location and field strength, and they seemed to sort of follow the cycle as well. Certainly the location, but our observations are very far apart, so they don't so much follow a cycle when we phase fold them, but generally they seem to follow the trend we'd expect.
Okay, thanks.
I guess that's because in any given cycle, you only really have one observation.
Yeah.
Yeah, they're quite sparse as well, right, at the moment. So are you planning to do some follow-up of this star?
There are additional observations taken with NeoNarval, but we sort of ran out of time to include them, and we couldn't. There was issues with the normalization, so I'm not. That's sort of sitting with in the to-do basket. Yeah.
I saw that Alexei temporarily had your hand up. I don't know if that was the question you were going to ask.
I got my question stolen.
Okay.
Maybe I can say amazing talk.
No.
Oh no! But maybe if you can show us the plot on slide 13 when you have the period and your observations. So the additional observations that you have, would they fall in a cycle that could allow you to constrain the period a bit more, or is it also bad luck that?
13. Oops, I might have to go back. This one?
Exactly.
From memory, having had a quick look at them with the poor normalization and stuff, they don't actually show any additional polarity reversal. But actually, we do have two observations that were in late 2006, which we didn't include because we couldn't really get a map that's reliable with two observations. But the Zeeman signatures, at least, seem to be opposite those in 2007. So it's possible that there's an additional polarity reversal there earlier in the piece.
Okay, but it's amazing what sampling does, right? Like if you just look at the bottom row, you just feel it's a long cycle.
Yeah.
Yeah. Cool. Thanks.
Any more questions? If not, then thanks again.